Let's begin our discussion on velocities of points on an extended body. And the first thing we want to take a look at is relative motion. And we're going to make a relationship between relative motion and the angular velocity of a rotating object, or an object which is undergoing rotation and translation. And one of the things that we really want to concentrate on is the whole idea of objects that are rolling. So let's refresh our memories on the whole concept of relative motion. Let's assume that there is an origin in the classroom in which you're sitting. Then your position and another person's position can be related both to the origin and to each other. So the position of student A with respect to the origin, which might be written this way, is equal to the position of student B with respect to that same origin, plus the position of student A with respect to student B. And so this relationship holds, again, if you take a look at the subscript notation, A over O is equal to B over O times A over B. And so the B's cancel out. That's the easiest way for relative positions or velocities to become apparent as far as what order is which. You know, how do I know whether it's A equals B plus A over B, or B equals A plus A over B, or whatever the case might be. Just look at those relative motion fractions, if you will, and they'll kind of give you a really good idea of what order they should be in. Well, if I take the time derivative of this first line, I'll get the second line, which is velocities. As a matter of fact, I can take the time derivative of the second line and move to accelerations, but we'll do that later on. All right, let's take a look at a rolling solid. So let's say I have a surface here, and we'll take a wheel, because it's the easiest thing to work with. And the center of that wheel would be some point A, and then we'll look at this point on the bottom as point B. Now the velocity of A, if the wheel is rolling to the left, the velocity of A will be to the left. And this would be the velocity of A with respect to B. And so I can write the velocity of A with respect to B. Here's the position vector of A with respect to B. So the velocity of A with respect to B is the derivative of the position vector of A with respect to B. But that velocity is also equal to omega, where omega is the angular velocity of this rolling object. So this is the angular velocity of the wheel, and that is a vector quantity. Now, in order to know the direction of that vector quantity, okay, so keep in mind the right-hand rule, curl your fingers in the direction of the rolling, which is counterclockwise, and your thumb points out of the page. Not the best right hand on the planet, but that'll give you an idea. So in this case, if the object is rolling to the left, then omega is in the positive k direction, where the I hat direction is to the right and the j hat direction is up. So the positive k direction is out of the board. So the velocity is equal to omega times the position of A with respect to B. And that makes a lot of sense. You've got an object here undergoing this rotation. If you're a point at the bottom of the wheel, or better yet on the ground, you're going to see A move to the left. And so we know that that's going to hold. So let's keep in mind the cross product then. So the right-hand rule says if this is in the k hat direction, it uses a very simple case where r is in the j hat direction. K cross j is equal to minus I hat. And indeed, this is moving to the left, and that's in the negative I direction. Okay, let's remember our I, J, K circle. I goes to J, J goes to K goes to I. So K cross J is going in the wrong direction, and K cross J goes to I, but since it's in the wrong direction, we get the minus sign. So if I have an interest in the velocity of A with respect to some origin, then using my relative motion equations from the previous slide, the velocity of A with respect to the origin equals the velocity of B with respect to origin, plus the velocity of A with respect to B, where A and B are on this rolling object. So this is omega cross R AB. So let's take a look at this example. This will give us a real good idea. What we're going to do is we're going to start by looking at the velocity of b with respect to a. Now the beauty of this, if I take the velocity of b with respect to a, that's going to equal omega of the bar AB, so that bar right there, so that's the omega of AB, crossed with the position of b with respect to a. Okay, so I'm going right back to this whole equation. Omega is, in this case, the angular velocity of that bar. Alright, so the velocity of b with respect to a equals omega of the bar AB crossed with the position of b with respect to a. But omega AB, you'll see that that's 6 radians per second in the counterclockwise direction, so that's a positive 6 radians per second in the k hat direction. So 6 seconds to the minus 1 k hat. That's my omega, and I'm going to cross that with the position of b with respect to a. But the position of b with respect to a, if I let this be the I direction and this is the j direction, the position of b with respect to a is 0.32 meters in the I hat direction. So 0.32 meters in the I hat direction. And if I work that out, that's 1.92 seconds to the minus 1 meters. So that's meters per second, I, j, k. And so k cross I yields j. And it's in the correct direction, so that's a positive j hat direction. So this would be 1.92 meters per second in the j hat direction. But we can see that makes a lot of sense. If this thing is rotating at 6 radians per second in the counterclockwise, while it's in this position, b is directly to the right of a, b must be moving straight up. So 1.92 meters per second in the j hat direction. That's the velocity of b with respect to a. Now I should point out in this example, a is basically my origin. It's a fixed location. Alright, so now let's find the velocity of c. That's what we're looking for, the velocity of c. So the velocity of c implies the velocity of c with respect to the origin. And in this case, a is my origin. So the velocity of c with respect to a, that's what I'm looking for. That's going to be the velocity of c with respect to b plus the velocity of b with respect to a. Look at your subscripts, c over b, b over a, the b's cancel, and you're left with c over a, which is exactly what you want from right there. Well, I already know what the velocity of b with respect to a is, so that's the velocity of c with respect to b plus 1.92 meters per second j hat. So what's the velocity of c with respect to b? Well, the velocity of c with respect to b is going to be omega. Now, omega of what? Well, in this case, it's the omega of the bar that contains both point B and point C. So it's going to be omega of this bar right here. So I'm going to call that omega BCD. So omega BCD, that's a vector quantity, crossed with the position of C with respect to B. Now the position of C with respect to B, here's B, there's C, so it's 0.24 meters to the right and 0.48 meters up. So 0.24 meters in the I direction plus 0.48 meters in the J direction. Now I don't know what omega BCD is, but I do know it's got to be in the K hat direction. So if I write this out in determinant notation, the cross product becomes ijk along the top row, 0, 0, omega BCD in the second row, and in the third row I get 0.24 meters, 0.48 meters, and 0 meters. So there's my determinant. And so this is going to equal, in the I direction, we cross out the row and the column containing I, and then it's 0 times 0, so that's just 0. There's an I hat out front. That's from right there. Minus 0.48 omega BCD. 0.48 meters omega BCD. That's the first part of the determinant. Then I cross out the column and the row containing J. And so it's going to be J hat. But remember that J hat plus, minus, plus j hat has a negative sign out in front. 0 times 0 minus 0.24 meters times omega BCD. Finally, I cross out the column and the row containing k, and I'm going to get 0 minus 0, so that's going to be nothing. So velocity of c with respect to b turns out to be minus 0.48 meters omega BCD plus, because you have a minus sign here and here, 0.24 meters omega BCD. Okay, so let's now look at the velocity of c with respect to a. So the velocity of c with respect to a equals the velocity of c with respect to b, which is right here. And I forgot there's an I hat here and a j hat there. So minus 0.48 meters minus 0.48 meters omega BCD I hat plus 0.24 meters omega BCD j hat. But then I have to add to that plus 1.92 meters per second j hat. Now I've got too many unknowns. I don't know the x component or the y component of that, and I don't know omega BCD. But if we take a look at the original diagram, c is forced to move only to the right or to the left. So there's a constraint on c. It can only move in the I direction. Given that, the j component must be 0. So here is the j component. So I can say that 0 equals 0.24 meters omega BCD plus 1.92 meters per second. That's the j component. And so minus 1.92 meters per second equals 0.24 meters omega BCD, and therefore omega BCD equals minus 1.92 meters per second over 0.24 meters. And that's a minus 8. Meters cancel. I'm left with 1 over seconds. Seconds to the minus 1. And so omega BCD is minus 8 seconds to the minus 1. That's clockwise. Right? The minus sign is clockwise. Let's take a look at that. If this is moving up, that's going to force c to the right, and so BCD would be rotating in that direction. Kind of show that to yourself for a little bit. I think you'll see that happening. And so that means that the velocity of c with respect to a is equal to minus 0.48 meters minus 8 seconds to the minus 1 in the I hat direction. And that's going to be minus a minus is positive, and 8 times 0.48 is going to be 3.84 meters seconds to the minus 1 meters per second in the I hat direction. So it's in the positive I direction. 3.84 is in meters per second. That's a velocity. That's good. And as I push this up, that should be moving to the right. So that gives me the correct answer for the velocity of c, or at least a sensible answer. All right, let's take another look at a different example here. Very similar example, but we want to know the angular velocity of the scoop given that omega BD is 1 radian per second clockwise. So BD is moving in that direction. So that says that omega BD is equal to minus 1 second to the minus 1 in the k hat direction. In the k hat direction. So that's a vector quantity, and it's clockwise, hence the minus sign here. And what we're interested in is the angular velocity of CE. Now what we're going to do is we're going to take advantage of a couple of different things. First off, notice D and E are both fixed. So let's call D the origin. So the velocity of B with respect to D, that's just going to be equal to omega BD, which I know, crossed with the position of B with respect to D, which I also know. Then the velocity of C with respect to D is going to equal the velocity of C with respect to B, which I don't know, plus the velocity of B with respect to D. which I do know because I'll be able to calculate all of this. But here's the deal. The velocity of c with respect to e will equal the velocity of c with respect to d will also equal the velocity of c with respect to e plus the velocity of e with respect to d. All right, look at your subscripts. The e's cancel and you're left with cd, both sides. But the velocity of e with respect to d is 0. E and d cannot move with respect to each other. So that goes to 0. So what that says is that the velocity of c with respect to d equals the velocity of c with respect to e. And I'm going to take advantage of that relationship. So we'll start with the velocity of b with respect to d. That's going to equal minus 1, second to the minus 1, k hat, crossed with 1 foot in the I hat direction plus 2 feet in the j hat direction. And that's 2 feet per second in the I hat direction minus 1 foot per second in the j hat direction. Then the velocity of c with respect to d equals the velocity of c with respect to b. Now that's going to be I, j, k, 0, 0, omega bc, which I don't know. But then the position of c with respect to b, that's 2.5 feet in the I direction right here. And then down, this is 2 feet, this is 1.5 feet, so it must be down 1/2 foot. So minus 0.5 feet in the j direction and nothing in the k. So that's the velocity of c with respect to b plus the velocity of b with respect to d, which is 2I minus 1j feet per second. So this is going to equal 1/2 foot omega bc in the I hat direction. Okay, that comes from crossing out my I get 0 minus a minus, because there's a negative sign there, 0.5 feet times omega. Cross out my j, I'm going to get 0 minus 2.5 feet, but then j is negative, so plus 2.5 feet omega bc in the j hat direction plus 2I minus 1j feet per second. Then I'm going to take advantage of the velocity of c with respect to e. That's going to equal omega ce, which is what I'm looking for. That's in the k direction. I don't know if it's positive or negative. Crossed with the position of c with respect to e, but that's 1.5 feet in the j hat direction. And so this will equal 1.5 feet omega ce, and k cross j is negative I. So I'm going to put a minus sign out here and an I hat there. And then I'm going to take this term and this term, and you notice there's two unknowns, omega ce and omega bc. I'm going to set them equal to each other. But I know that this is really two equations, because I'm going to set I equal to I and j equal to j. As a matter of fact, I can see that there is no j component for omega ce. So if I look at the j component right in here, I've got this term plus this term. So that tells me, looking at the j component, 2.5 feet omega bc minus 1 foot per second equals, there's no j component here, so that must equal 0. And so I know that omega bc equals 1 foot per second divided by 2.5 feet, which is 0.4 seconds to the minus 1. Then I'll substitute that into here and solve for omega ce. So I have 1/2 foot omega bc, but omega bc is 0.4 seconds to the minus 1. Okay, that's this term right here, 1/2 foot times omega bc, but that's 0.4 seconds to the minus 1. That's the I component of velocity of c with respect to d. and the I component of the velocity of c with respect to e is right there, minus 1.5 feet, omega CE. So it has to equal minus 1.5 feet, omega CE, and so I get 0.2 feet per second equals minus 1.5 feet, omega CE. The feet will cancel. I have 0.2 over, and that's seconds to the minus 1, over minus 1.5. That's minus 0.133 seconds to the minus 1. Minus sign indicates that it must be clockwise. And indeed, if this is rotating in that direction, B is pushing C to the right. That's going to make it rotate in that direction. So it all makes sense.